23 is on extreme values of functions. So extreme values basically just means maximums and minimums. Okay, so I have drawn out a picture with everything you could ever expect with these types of questions. Okay, so we have something with an open circle, that would be no maximum there. We have a local maximum. That just means in that general area, if I drew like a little circle around it, it is the highest point in that general area. Do we agree with that? We call that a neighborhood. We would not have a minimum here because there's no point there. This would be a local max because if I draw a circle around it, it's the highest point in that general area. So what do we think the difference between local and absolute? What's the absolute highest point on the graph? Yeah?
The highest it will ever go?
Yeah, the highest it will ever go. So this is the highest point on the whole graph. So it's both an absolute and a local maximum because of that. There is no absolute minimum though. Huh? If there's an open circle, there is no absolute or local. And then since this goes all the way down, do you guys see that? That's going to be no absolute minimum because it goes off forever.
So is the absolute always a local as well?
Yes. And then there's things like x cubed. You guys know the parent function for x cubed, how it kind of tapers off and then goes up like that. It looks kind of like it would be a max or a min, but it's actually neither. Okay, it kind of starts out as a maximum, and then like if I only looked at just this part and I continued it this way, it would be a maximum. But if I only look at this part and I continued that way, it would be a minimum. So it's neither a max nor a min. Okay, but it is still a critical point. Yes. So see how there's the f prime at that point is equal to 0. Okay, so f prime is equal to 0, but it's neither a max or a min. So there can be lots of weird things. We can have the derivative equaling undefined, and there can be a maximum. Do you guys see where that happens? At corners and cusps. A critical point is what we're going to be talking about today. So critical points are something interesting is happening there. The derivative is equal to 0 or it's undefined. All right. So it says a function f has an absolute max, or sometimes you might hear it called a global max, if f of c is greater than or equal to f of x for all x values in the domain. So if some y value is the highest y value of all. And same idea for the absolute minimum. If it's the lowest y value of all, then it's the absolute min. You guys paying attention back there, Kyle? So we call the maximum and minimum values extreme values. So if you see extreme values or extrema, it's the same thing, maximums and minimums. It should be maxima and minima, but I will always say maximums and minimums. All right, so a function has a local if in that general area, we call it the neighborhood. As long as you're around that area, it's the highest point. So it's like the hills and valleys, okay? So let's try one. So it says find the local maxima and minima in the following function. Is there an absolute max or an absolute min? So local minima. So we talked about this in pre-calculus. We always say the maximum is the highest, like it's the y value that we go to, and the highest y value, and the minimum is the lowest y value. So if I'm talking about a local minimum, it's going to occur here and here. And I would write it by saying -7 at an x value of -10, because we're talking about how high or low we go on the graph. All right, so the next one, our local minimum would be -3, and it occurs at x equals 4. Okay. So when I say of these values, these are y's. So the local maxima. The local maxima is going to be just 1 point. Do you guys see where it is? Right up there. So we're going to say it's 9 at x equals -5. Okay, so are any of these, do I have an absolute max or an absolute min? What do you think, Grant?
You have an absolute minimum at that -10.
Yes, exactly. So this absolute min, we would say of -7 at an x value of -10. Okay, so this one's the absolute one. Why not a maximum? Yeah, Louis? It goes up past it. So even though I tried to draw it, do you guys see how I drew the arrows? It was like below, so it kind of looks like it's going to be the absolute. It actually does extend past that, right? So we don't have an absolute max. So it says find the maxima and minima, local and absolute of the following functions. So this is where we're going to use our calculus. So we want to know where our derivative is either equal to 0 or where it's undefined. That's the possibilities, okay? So I'm going to do f prime of x equals 3x squared minus 6x. And I'm going to set it equal to 0. I can pull out a GCF of 3x, and when I do, I have x minus 2 left. So I get two critical values, 0 and 2. So I'm using the word critical value, places where our derivative is equal to 0 or undefined. So what we do on these problems is we put them on a number line, 0 to 2, and we're going to test in f prime. So when I test in f prime, I'm going to test numbers in each interval. So we've talked about critical values in even algebra 2, right? And we had critical values on a number line, and we tested in each interval. Okay, that's what we're doing here. So I'm going to test like -1. So when I plug -1 in, I get 3 times -1 is -3, -1 minus 3 is -3, -3 times -3 is +9, so it's positive. We're just worried about whether it's positive or negative. So when I plug in 1, 3 times 1 is 3, 1 minus 2 is negative, so positive times negative is a negative. And then when I plug in 3, I get positive, positive, so positive. Do you guys all see what I'm doing there? So this means that my original function is increasing, then decreasing, then increasing, because these little pluses and minuses mean my slope is positive, then my slope is negative, and then my slope is positive. Yeah, great.
But if you're plugging into the f prime, couldn't you also plug it into the one above it?
You could. It's just going to be easier to plug into the factored form because you're just going to have like a bunch of positives and negatives multiplied together.
But if you plug 3 into this factored form, you get a, I don't know,
Yeah, you should get the same thing. All right, so what I always want you guys to do is use your knowledge of graphs to verify whether or not this is true. So we know x cubed graphs, it could look like the parent function, it could look like that. But couldn't it also like go up and then come back down, like something like that? That's what this one does. So see how we have an x cubed function originally? It goes up, it comes back down, it goes back up. There's a maximum, then there's a minimum. Okay, so we have a minimum at the 2, and we have a maximum at the 0. So basically, I'm going to have a maximum when my function is increasing and then decreasing. There has to be a maximum up there. Okay, and then I have a minimum when I'm decreasing and then increasing. Okay, so let's write out what they are. So we're going to say a max of something at x equals 0 and a min of something at x equals 2. So how do you think that I find how high or low they go? Go back into the original, right? So I'm going to do f of 0 and I'm going to do f of 2. What if I made a mistake and plugged them into the derivative? What will I always get? I'll get 0, right? Because I just found where f prime equals 0. Right, so if I plug in 0 to my original, I get 0. If I plug in 2, I get 2 cubed minus 3 times 2 squared. So -4. All right, so I have a max of... So at 0, I have 0, and at 2, I have -4. All right, so let's talk about these. Are these local, absolute, or both?
They're both
local max and local min, right? I don't have any absolute. Why? Because there were no endpoints, and it was one of those ones that went like that. It went off forever. Okay, so it's a local and local. Okay. Yes? Do you have a question?
How do you know if this one that goes on forever?
Because there was no, like, a lot of times we'll have intervals. This one didn't say on a certain interval. So a normal x cubed function, we know, like the end behavior, we know the ends go like that, right? Remember that? So the ends are going to go forever. We could. We have multiplicity too, it looks like, right? At x equals 0, so that's why 0 like touched. So it went up, it touched there, it went back, and then it went like that. So if you remember the multiplicity that we talked about in like in algebra 2, that's what's happening there. All right, but it doesn't have to be multiplicity. Like multiplicity is for zeros, x-intercept. It could have gone above the axis or below. All right, so sine of x. So sometimes I don't even need to do any calculus. Do we know what sine of x looks like? I hope so, right? What's the highest value and the lowest value? 1 and -1, right? So I'm going to start at 0, 0, and I'm going to go up. I'm going to come down. I'm going to go up. I'm going to come down, and it's going to continue, right? And it's going to go in that direction too. So this point right here, the slope is equal to 0 up there. So I could find the derivative. The derivative of sine is cosine. I could set cosine equal to 0. And I would end up getting x equals, well, let's think about where cosine is equal to 0. Whoops, didn't mean to do that. Cosine is equal to 0 here and here. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, right? All of those. All right, so these are these locations that I'm marking in blue. So I could have done that. I could have found the derivative. I could have set equal to 0, but we know what this graph looks like anyway. So at this first point, I have pi over 2, comma, 1. At the next one, I have 3 pi over 2, comma, negative 1. And then I have 5 pi over 2, comma, 1, because it has a period of 2 pi. So if I add 2 pi to pi over 2, I have pi over 2 plus 4 pi over 2 is 5 pi over 2, right? Mix with me? So if I'm talking about my maximums and minimums, are these local, absolute, both? What are we? They're both, right? It's actually local and absolute. Because the highest we ever go is 1. And it occurs at x equals pi over 2, and then I'd say comma, 5 pi over 2, comma, blah, blah, blah. What else could I write? Plus 2 pi k, exactly. Now on your AP test, I would write where k is an integer. Do you guys know how to abbreviate that?
K bracket.
K element z. Where k is an element of the integers. Okay, so if I was saying the local / absolute min, that would be of negative 1, and that occurs at 3 pi over 2 plus 2 pi k. All right, easy enough. So we can do that one without even. So like there's a lot that you don't even need to do the derivative of, like x squared. Where's its minimum? You guys know what x squared looks like. The minimum would be a 0, 0, right? So a minimum of 0 at x equals 0. What about a maximum? None, right? Does that make sense? So some of these things you don't actually need to do the derivative of. All right, so critical numbers. So a number C in the domain such that f prime of C equals 0 or f prime of C does not exist, okay? So we could have weird things. We could have places where we have a corner or a cusp. Okay, so it says you can have a maximum or minimum at critical values, but not always. So here are some examples to kind of keep in mind. So these are 4 examples in calculus that you always need to know, okay? Have in the back of your mind at all times, okay? So some of them we've talked about before, like y equals the absolute value of x. Okay, that's important because the derivative at 0 is undefined. But there's a minimum, right? So there's a minimum at x equals 0, though. Okay, so some people say, oh, minimums only occur where the derivative is equal to 0. Well, not necessarily, because that's the one we keep in our back pocket, right? We're like, oh, what about this one? All right, so x cubed. What's weird about x cubed? So some people say, well, whenever the slope equals 0, f prime equals 0, it's a maximum or a minimum. Is that true in this case? No. So f prime of 0 is equal to 0, but there is no max or min. And then x to the 1/3, do you guys know what x to the 1/3 looks like? It goes like this. And what happens for this one is temporarily, just like x cubed had a horizontal tangent, x to the 1/3 has a vertical tangent. It's the inverse of x cubed. So there's a vertical tangent. So that means that f prime of 0 is equal to undefined, right? It's undefined. But there's not a max or a min. So not necessarily always a max or min there. And then x to the 4th, this is kind of a weird one. It involves something that we call concavity, which we're going to talk about in the next few sections. So concavity, like for x cubed, see how this is down and this is up? Some people say holding water and not holding water. Like think about a bowl. It's concave up, we call it. So this looks like part of a bowl. It's concave up, and then this part is concave down. It's going down. So that's a way to kind of describe it. So like this would be concave up, and this is concave down. Absolute value of x is neither. So if I had something like this, down, up, down, up, down, up. Do you guys see concave up, concave down? And there's something called inflection points between them. So where it changes in concavity, I'm kind of guesstimating where these are, like that. Those are called points of inflection. And usually for a point of inflection, the second derivative, so we're going to take the derivative twice, will be equal to 0. Okay, but y equals x to the fourth is one that we keep in our the back of our mind because it looks kind of like y equals x squared. But if I take the first derivative, it's 4x cubed. And if I take the second derivative, it's 12x squared. Do you see how y double prime of 0 is equal to 0? But there's no inflection point, so no point of inflection. So I'm talking about that a little bit early. I forgot. I shouldn't have put it in this part.
Y prime of 0 is also 0, and just y of 0 is 0?
Yeah. They're all equal 0, yeah. All right. So it says find the critical numbers of the following functions. So we're going to take the derivative. We're going to set equal to 0 or undefined. So for this first one, I have f prime of x equals 3x squared plus 2x minus 1. It's never undefined. I don't have any square roots or denominators. So I'm going to factor, and it does factor. I need 3x and x, 1 and 1. And my outer and inner need to combine to be 2x. So I need plus and minus. So I'm going to do 3x minus 1 and then x plus 1. So I get two critical values. I get 1/3 and I get x equals -1. Okay, so all I asked here was to find the critical values. So we're good. We found the critical numbers, okay? Now, if I asked you to go further to figure out where it's increasing, decreasing, where I have a max, a min, and so on, like you could do all of that. You would put it on a number line, and you would test in each location on the right and left of 1/3 and -1. Okay, so this next one, I'm going to make it simpler to take the derivative, and I'm going to multiply my x to the 2/3 n. So I'm going to have 2x to the 2/3 minus x to the, this is x to the 1. So add my exponents, 2/3 plus 3/3, 5/3. Just because it's easier to take the derivative, I don't have to do product rule then. So I can just use my power rule. So as I take my derivative, I'm going to have 2 times 2/3 is 4/3, x to the -1/3, minus 5/3, x to the, subtract 1 from the power, subtract 3/3, 2/3. Okay, so I want to find when it's equal to 0 and when it's undefined. So it's a little bit messy. So what I have going on here is 4/3 x to the 1/3 minus 5 x to the 2/3 all over 3. And so what a lot of my students will do, and I'll show you this in a little bit, they set this equal to 0, so don't write this. And then they take this whole negative part and they add it over here and they cross multiply, which is fine. You get a critical value that way. But you lose the fact that f prime can also be undefined. That's also a critical value. So what I tell people to do in this situation is not to set it equal to 0, leave it as f prime, and get common denominators. So we're going to multiply by x to the 1/3 and x to the 1/3. So we get 4 minus 5, this would now be x to the 1, all over 3x to the 1/3. Because we need to find when f prime is equal to 0, but we also need to find when f prime is undefined. I shouldn't say equals undefined, but whatever. So for f prime equals 0, I'm setting my numerator. And so I get 4/5. But for f prime is undefined, I set my denominator equal to 0. So I get x equals 0. Both of those are critical values. So a lot of people think, oh, the undefined is not going to be a max or a min, but it could be. Remember, you could have those cusps, and this is a case where there would be a cusp. So you could graph that, and you'll see the x to the 2/3. This is another good one to have in the back of your mind. Y equals x to the 2/3 looks like this. Do you see how there would be a minimum there? Even though the derivative is undefined there. All right. So extreme value theorem. Okay, so the extreme value theorem, usually if things have names, like theorems have names, they're pretty important. This is a pretty important theorem. So the extreme value theorem says that if you have a closed interval, so we have n points, then there has to be an absolute max and an absolute min, okay? So, for example, like if I had y equals x squared, we said, oh no, there's not an absolute max. But what if I said I was on the interval -1 to 4? Then there would have to be an absolute max. Does that make sense? So we're talking about the endpoints as well. So it says if you have a closed interval, you have to check the endpoints as well. So for this example, it says find the absolute extreme of the following function on the closed interval. Use your calculator to sketch the graph and verify. So this first one, if I take the derivative, I get 12x cubed minus 12x squared. I set it equal to 0. I can pull out the 12x squared. I have x minus 1. So I get x equals 0 and I get x equals 1. So those are my critical values. Those are going to be what I put on my number line. But I don't want to do like arrows on the end of my number line. I want to do my endpoints. So I say, oh, but I'm only on the interval -1 to 2. So I kind of stop the number line. And now I do what I did before. I test in f prime, and I want to see if values give me positive or negative. So we like when there's, see how this is 12x squared? 12x squared is always positive. Doesn't matter what you're plugging in for, right? So that part's always positive. So I'm really just worried about the x minus 1. So if I plug in -1/2 to the x minus 1, I get negative. If I plug in a 0.5 or 1/2 into the x minus 1, I get a negative. If I plug in 1.5, I get a positive. So that means that this function goes downwards, then downwards some more, and then upwards. So it's going to look like one where it goes down, it tapers off to a slope of 0, it goes down some more, and then it goes up. And it has endpoints, but we don't know how high or low those endpoints are. So we don't know if this goes up above that other one or if it's below. So really on things where you're going to go back and plug into f of x anyway, you didn't actually have to do this up, down thing, right? But I know that I have possibilities. So what are my possibilities for the absolute max? There's 2 places that could be possible. -1 and 2, the endpoints, right? So this is going to be a max, and this is going to be a max. But I don't know which one's higher, so I would compare f of -1 and f of 2. But what about the absolute min? Do I know where the absolute min is? It has to be a min, 1, yeah. So this is going to be a min, and it's the absolute, definitely. But let's find what the y value is. So we go back in the original. If I plug in -1, I get 3 minus a -4, so 3 plus 4 is 7. If I plug in 1, I get 3 minus 4 is -1. And if I plug in 2, let me do that. Is it -16? I feel like I remember that number. Check that for me. 48 minus 32? Yeah. No, positive 16? Positive 16. All right, so which one's higher? 2. So that's the absolute one. So the question asked for find the absolute extrema. So we're going to say there's an absolute min of -1 at x equals 1 and an absolute max of 2, not 2, of 16, the y value, at x equals 2. Done. And there has to be. There has to be an absolute max and an absolute min because we were on a closed interval. There has to be a highest point and a lowest point. You could write the locals, and on the homework I think I asked for all of them. I tried to give you guys little like answer blanks on your homework so you don't have to keep writing out absolute max, absolute min. That's what takes a long time, so I try to do answer blanks. But I feel like last year I did an extra answer blank somewhere or I was missing one, so don't be surprised if that happens. I tried to be nice, but then that ends up being mean sometimes. So if I missed one, just add it in. All right. I try to edit each year, but I don't remember if I edited that. All right, so this next one. So if I have f of x equals 2x minus 3x to the 2/3, same idea. We take the derivative. So 3 times 2/3 is going to be 2, and then x the -1/3. And this is one where if we look at it, we see that we have to combine to get one big numerator, one big denominator, right? So I'm going to multiply by x the 1/3 on top and bottom. So I get 2x the 1/3 minus 2 all over x the 1/3. So if I set my numerator equal to 0, I get 2x the 1/3 minus 2 equals 0, so x equals 1. Do you guys see that? And then the other one is x to the 1/3 equals 0, so that's x equals 0. Oops. That's a 0. All right, so when we put both of them on the number line, we have 0 and we have 1, and then we're on the interval -1 to 3. Sometimes your interval doesn't even include one of the, like if I had gone from 1/2 to 3, then I'd only have one critical value, right? So sometimes you may not even have it, the 2 that you found, or 3 that you found. All right, then we test in each location. So if I try negative, I think I get positive. I'll do this really quickly. -1/2, yeah, I think I get a negative on top and then negative on the bottom, so it's positive on top, or positive together, I mean. And then if I try 0.5, I get a negative on top and a positive on the bottom, so negative. And then if I try something bigger, I get positive, positive. So it goes up, down, up. So 1 is a possibility for a max, or it's a possibility for a maximum. But the slope is undefined there. So what does that mean? I don't know. It could mean lots of things. Sometimes we have like something like this, right? A vertical asymptote. It's not a vertical asymptote, though. How can I tell based on my original that it's not a vertical asymptote? Is there a point there? If I plug in 0, what do I get? 0, right? There's a point there. So that's one of the ones where it's like a corner or a cusp, basically. Okay. So yes, there is a maximum at 0. And then I would want to compare it to all those other values. So I would actually have to find all of these because this is a possibility for the absolute min. This is a max, min, and max. But I don't know which one's absolute. So I'd have to find each of those things. And I don't remember what each one is. So, but I think it's time for you guys to go, isn't it? So let me check. New day.
45.
Yeah, so let me pass out the, oh, it's an 8A, isn't it? No, I'm really confused. All right, so let me stop there.